My title is Effect of Microscopic Structure on High Cycle Particle Damage in Polycrystalline Nano. So, first, let me refresh your memory on the particle mechanism in metals. When a cyclic load is applied to the metal materials, persistence band PSB is generated. Inside this PSB, you can find ladder-like structure which is formed by self-organization dislocations. On the other hand, on the surface, the PSB introduces intrusions and extrusions. It is widely known that the size of this fatigue substructure is about 1 micrometer, which is independent of material size. And it is also known that the PSB plays an important role in fatigue fracture because fatigue cracking is generally initiated at the PSB. By the way, latest electronic devices contains a lot of small metals with the size of less than 1 micrometer, for example, metal lines. Of course, these electronic devices are subjected to external mechanical vibration or cyclic thermal stress. But there is no space to hold the PSB because the PSB is too large. So we thought these very small metallic material had characteristic fatigue behavior. So in the previous study, we conducted a resonant fatigue experiment for small metal material. This is a specimen. This is a weight to reduce the resonant frequency. And the test section is located here. In this experiment, the specimen is oscillated like this. In this experiment, we found characteristic fatigue damage, which was very similar to the PSB, but the rise in nanometer scale. And the formation stress was much higher than that counterparts. So this result indicated that the very small material has a characteristic fatigue behavior. So in this work, as a next step, we interested in the high cycle fatigue behavior of polycrystalline metals. When an external load is applied to polycrystalline material, microscopic stress field, which is due to the deformation constraint between grains, will appear inside the material. So we thought this effect of microscopic field must affect the fatigue damage in nanopolycrystalline metal. So the first step, so we prepared a nano-component specimen which has nanopolycrystalline metals, and we conducted fatigue experiment. Okay, first of all, we prepared a multi-layered material. And this is a cross-sectional image. And as you can see, the copper is sandwiched by a silicon nitride layer and silicon substrate. And from this material, we fabricated the specimen by FID processing. First, we cut the block from the material and picked up this one. And a block is mounted on the silicon substrate. And this is the gold weight to reduce the resonant frequency. We mounted this block on the silicon layer, silicon nitride layer. And we shaped the test section. And after this processing, to remove the damaged layer introduced by FIP, we performed aluminum ion beam processing. This is a SM image of the specimen. This is a gold weight. And the test section is located here. And the test section is composed of silicon nitride, copper, and silicon. And cross-section of this part has a trapezoidal shape. And before the experiment, we want that in order to obtain the crystallographic information of grains in copper portion, we performed electron backscatter diffraction analysis. This is EBSD image, and we found 13 coarse grains. So we numbered these 13 coarse grains from 1 to 13. And from the result of EBSD, we draw stereographic projections of 13 grains. And as you know, the copper is FCC metal, so it has 4 slip planes and 6 slip directions. So in this projection, we denoted 4 slip planes as A to D and 6 slip directions as 1 to 6 in accordance with Schmidt and Bose notation. In this notation, the primary slip system, which has the largest Schmidt factor, is expressed as B4. B means primary slip plane, and 4 means primary slip direction. Okay, so in the experiment, we modulated the specimen by a piezoelectric actuator, and the displacement amplitude was measured by a laser Doppler vibrameter. Before the experiment, we preliminarily measured the resonant frequency of the specimen, and by using this resonant frequency, we conducted fatigue experiment and constant displacement amplitude. And in this experimental method, if fatigue fracture is produced to the specimen, the displacement amplitude will suddenly decrease. So first, we applied the specimen. We applied the small displacement amplitude to the specimen up to 10 million cycles, and there is no change in the displacement amplitude. We increased the displacement amplitude, and the specimen was oscillated again. And during the experiment, if we found rapid decrease in the displacement amplitude, we finished the experiment. Okay, this slide shows the experimental results. This is a relationship between the displacement amplitude and number of cycles. As you see, at the smaller amplitudes, there is no change up to 10 million cycles. However, at the displacement amplitude of about 10,200 nanometers, the displacement amplitude rapidly decreases like this. So after the experiment, we measured the resonant frequency, and the resonant frequency was shifted like this. So we judged that the fatigue damage was introduced to the specimen. So from the SEM image observation of the specimen after the experiment, we found characteristic localized slip band like this at a certain area in the sleeve portion. From the EBSD map, these slip bands were generated in the grain sleeve. And from the stereographic projection of the grain sleeve, this slip band was due to the activation of slip system P4. Like this, this specimen showed characteristic high cycle fatigue behavior. We examined this fatigue behavior from the viewpoint of the Schmidt factors. These are the Schmidt factors of slip system P4. in the 13 grains. As you see, the grain 3 doesn't have the highest value. This result indicated that the Schmidt factor cannot explain the fatigue behavior. So as the next step, we focused on the microscopic storage field due to the deformation constraint between grains. This is the analytical model. In this analytical model, we reproduced each grain in the same portion on the basis of the EBS demand. And we considered the anisotropic elastic property of each grain. So we inserted these elastic constants into each grain. Okay, so this is a Schmidt factor of P4, which was shown you in the previous slide. On the other hand, the bottom one is the results obtained by FEM analysis. This is maximum resonant shear stress. As you see, grain 3 has the largest value, and the slip system is P4. This result suggests that this C portion has a stress condition where the slip system P4 in grain 3 is preferentially activated. So these results have a good agreement with the experimental one. So from this experimental and analytical result, it is found that the microscopic storage field in the nano crystalline copper is strongly affected the high cyclic fatigue behavior. Okay, these are the conclusions, and thank you for kindly attention.